For our next exercise, we'll create a simple particle system. So first I will open the project generator and I will pick the project path of the folder where I want project generator to store the exercise. It will be my GMCOF folder, open, and I'm going to call this exercise 5 particle system. Okay, and generate, and now it's saved in the right folder with the right name. So I will open in IDE, and project generator will open Xcode for me. So okay, here we go. We have our usual configuration of Xcode. There's a little error message there, but I wouldn't pay attention to that because the project hasn't been run yet, and running will probably clean that up. So what I want to do is to create a new class. So we'll talk more about class in our classes, meaning, sorry for the redundancy, but in our teaching classes we will talk about classes. So classes, basically, they're like an ontological way to define these entities, right? The class being kind of the conceptual template for the different objects. So an object is an entity that shares characteristics with other entities, so they all belong to that same class. And if we change the class definition, all the entities in kind of change how they behave. So, you know, usually when we talk about object-oriented programming, we talk about classes and objects. We refer to the object, to the natural world, as a kind of an ontological metaphor or some resemblance to this idea of classes and objects that, you know, for example, dogs. Dog is a class, right? And then you have multiple, you know, millions of dogs, thousands of dogs. And you have dog Pluto or dog Scooby-Doo, or, you know, and they all share the same characteristic, the same core characteristics. Let's say they all have 4 legs and they bark, but then there's variations. Each have their own individuality, each have their own name, and that's what makes them objects. But the main category is the class, right? So for a particle system, we're going to create dozens, hundreds, maybe even thousands of particles. They're all going to behave in a similar kind of way. We don't need to code them individually, right? It would be a nightmare. So we're going to create a class particle, and then we're going to have each individual particle. We're going to have particle 1, particle 2, particle 3, particle 4. They're going to be objects of the class particle. So let's go ahead and create a class. So file, new file. Make sure, before we do that, make sure you have the SRC folder selected, or that you're inside that folder, because that's just going to make it easier to create the files in the right place. Otherwise, then you need to move them, to drag them. So file, new file. I'm going to create a CPP C++ file. Okay. Make sure you're in Mac OS, not in iOS or watchOS, if you're at Mac OS, and that's a CPP file, and that you're inside of the SRC folder, right? So next, we're going to name our class, and I'm going to call this particle, right? And we're going to also create a header file. That means we're going to have the CPP file and also the H file, okay? And just let's make sure that we're saving this in the source file of the particle system. Exactly, that's correct. And targets is the particle system, and the group, which is this little folder in the Xcode, is SRC. We had this all predefined, so it's just going to the right places. I'm just double checking with you. Okay, so create. So now we have a new CPP file and a new header file. Xcode calls it by default HPP. It's the same thing. You can rename it if you want. I would leave it. It's the same. It's the same thing. So let's just clean up the code a little bit. In our particle CPP, it says include particle HPP. I'm just going to remove all the comments that were left there. By accident, I created a breakpoint. If you type in a number, you create a breakpoint. If you see this blue thing, just remove it. We can talk about breakpoints maybe in class to discuss debugging techniques. Okay, so that's particle CPP. What about particle HPP? Now, particle HPP has some kind of precompiler directives here. This if not def particle HPP, then define particle HPP. It's a precompiler instruction that says anything which has not changed, you don't have to compile, but or to recompile, but what has been changed, then recompile. And I don't like this syntax. I prefer the Pragma 1 syntax. Actually, I prefer a lot of the code that we have in our default of app H. So let's just go ahead and copy that. So I'm going to copy the Pragma 1's, the include of, we're going to need it actually, because we're going to need openFrameworks code, the setup and update and draw structure. We're going to need all that. So I would copy lines 1 and 10 to 10 of our of app H, and I would paste them in particle HPP. I'm just going to remove all this code here and then paste. Oh, I did a wrong copy here, so probably didn't press Command C correctly. Now I pressed it correctly, and now I go to particle CPP. No, sorry, particle HPP, and I'm going to paste that code here. So this line 1 is fine, line 3 is fine. Now line 3, this is not class of app extends public of base app. We're not extending anything, so we just need the name of the class here. And the name of the class that goes in there has to be the same as the file name. So in this case it's particle, right? Particle. Okay. And then it's going to have a public setup, update, and draw. And that's fine. So to a certain extent, when we close the class, don't forget to put a semicolon after you close the class. Usually we don't put a semicolon after closing the curly brackets in if clauses or in for loops, but in a class you need. And sometimes the error persists because Xcode takes a while to adjust to the changes you've made. Okay, so this is done. Now we need to go to CPP and add those functions here. So it was void, and then it's particle. And now you need the scope operator, which is this double colon, particle setup, sorry, small setup, and then we will define what the setup does in here. Then we need a void particle update. So this double semicolon just tells us the scope. We're defining setup for particle because we're outside of the H, we're outside of the strict class definition, but we're still defining that class in a separate file just for the sake of tidiness. That's how we do things usually in C++. Particle, we have draw is still missing. Particle draw. So it's the function setup of the class particle, the function update of the class, and they are all void functions. Now we have our basic class setup. In draw, I just want to put some kind of dummy function here that will do something so that we can perceive that the class is working. So here I'm going to say, I'm just going to draw a circle of draw circle, and the circle will be pixel 100, 100, and of radius 50, let's say. Okay. Okay. So that's it. That's the only thing this class is going to do for now. is draw a circle. And now in of I need to use the code of those files, particle HPP and particle CPP. I need to include those files so that that code becomes accessible to this file of app, right? So include particle this is HPP. Right? Again, HPP and H is exactly the same thing. They're header files. It's similar extension name. Okay, so far so good. Now in of app H, I want to create a new object of that class. So I'm going to say particle, and now I'm going to create an object, my particle. Okay. Now we have the object particle of the class my particle. So I don't think I've mentioned this, probably mentioned it in class as well. Naming conventions. So when we're naming objects, we saw naming conventions a while ago for constants. So the previous exercise, if I'm not mistaken, which is all caps and underscore a space. So when you're naming objects, the case convention is camel case, meaning that the first letter is lowercase, then you concatenate, you merge the different words. If you have the words my space particle, you merge them together, remove the space, and the second letter becomes capitalized. The initial of the second letter becomes capitalized, and so on and so forth. If you had more words, that makes it a bit more readable, and it's called camel case because it goes up and down. The case goes up and down like a camel hump. Yeah. Okay. Small detour. We have a particle. Now we can draw it, right? So if we have a particle, we can draw that particle. We can say my particle draw. Okay, so very basic, but I just want to prove that it's a proof of concept that from the class of app, I can communicate with the class particle. Actually, I can command class particle from the of app. Let's see if this works fine. It might take a while because it's the first time we're compiling this exercise. And once we have this communication going, we can create multiple particles. Here we are. We have this particle being drawn. So of app is commanding particle to draw, and particle in the draw we have an off circle. As you can see, these circles have this kind of jagged look that we can remove, like we've seen before, by of set circle resolution to 100, for example. Great. So now maybe I'm going to set the background of background, set it to black. Great. So now we can have this particle doing something a little bit more interesting. Let's create some animation in the particle. So let's have the particle have some kind of velocity so that it will move. And this velocity can be random, so that when we have multiple particles, they all move a little bit differently. But let's animate one particle first, and then let's generate multiple particles, right? So let's go to our CPP. And as you can imagine, as we saw in the previous exercise, I like to use vectors a lot, vec2s in this case. So I want to have a vector for the position of the circle, and I want to have a vector for the velocity, which is the increment each frame that this particle will move, right? So particle HPP, let's create here two vectors. Let's create GLM vec2. Let's create pos v, so the position vector, and GLM vec2 velocity vector. Okay, I'm going to call it val or val v for the velocity. Great. So in setup, we're going to define what the initial position will be, and we're going to define what the initial, or what the velocity will be. For now, velocity will be constant. So let's maybe let's say that GLM pos v equals, sorry, we don't need GLM here. Pos v equals the same, 100, 100. And val v equals, I'm going to make this particle move towards the right. So let's add 5 pixels per frame and 0 pixels per frame. And I didn't mention I wanted to make it random, so maybe what I can do is of random. You saw of random in the last exercise. So of random between 5 and, or between, I don't know, 5 and 10 maybe. And then in the y-axis, let's have it be 0. Okay, and then on update, we have to say that the position v gets incremented by the velocity v. Okay. Actually, for later, we can say that val v is velocity vector. Oops, velocity. Just for later, we impose v is the position vector. We're going to say that the position gets updated by the velocity, right? And then we're going to draw the circle in the position v. Okay. So we can draw a circle in a number of ways. One is use xy coordinates. We can use a 2D vector. We can use a 3D vector to draw a circle. And I guess that should be it. We're going to have an animated particle going to the right, because only the x is being incremented to the right. And but we need to realize something. We're drawing the particle, but we're not updating or setting up the particle. So we need to do that. Otherwise, what's in setup doesn't get run, and what's in update doesn't get run. So we need to do my particle setup. Sorry, my particle dot setup and my particle dot update. Right? And we're basically replicating the conventions of openFrameworks inside the class. So the main setup runs, if you have multiple classes, we're going to set up all the classes. In the update, we're going to update all the classes, and in draw. So the of app, this is a great way to structure more complex applications where your main class is basically just the traffic controller that sends information between the classes, that triggers the classes, starts them up, kills them, manages them, and then all the mechanics are kind of dealt by the different classes. So we have a main class which is kind of the dispatcher between the different classes, right? And I see it as a traffic controller of information, the kind of arbiter between the different classes. Okay, so now if we don't have any bug in the code, the particle will be set up, meaning that all those initial values will be created, position and velocity, then it's going to be updated, and then it's going to be drawn. And it's not moving. That means I have some error in my code. It's not velocity plus position plus velocity plus pos f plus equal velocity. Sorry about that. Because otherwise it just adds it once, right? But we want it to keep being added. So this is the same as position v equals position v plus velocity. Okay. Here we go. So apologies for that, but it's actually good that I made this mistake, because it kind of sets the reminder to me to recap that pos v plus equals, this is the same as pos v equals pos v plus vel v. Otherwise, it just adds it once, right? This way, with this formula, if I had the code I had before, which is pos v plus vel v, it just adds it once, and there's nothing. It doesn't. Nothing gets done. It just gets calculated once, and here it adds it reflectively. So the animation is done, which is great. But as we saw, the particle goes right, and then it disappears, which for now it's fine. I'm not going to worry too much about it. What I'm going to do next is to have not just one particle, but multiple particles appearing all the time. Okay, and that's a big kind of conceptual jump. Actually, before I do that, I want to show you something, how to send values through parameters. So let's imagine that you want to set up each particle with the y of the mouse. Instead of being constantly this 100, 100, 100, let's say that the y, you want the y to be the y of the mouse when you set up the particle, right? So what we could do here is on setup to define some parameters on setup, right? So we could have on setup of the particle, we could say that we're going to receive a glm vec2, which will be the origin vector, which is going to be defined by the mouse. Okay. And here in setup, we're gonna also, in the setup of the particle in the CPP, we're also gonna say glm vec2 origin. We're gonna copy that code, right? Origin. And then position v, the original position will be equals to, I think I called it origin v. Let me just double check. Origin v, yeah. And position v equals origin v. Now, when I set up, I can already set it up from the onset with a certain vector, which is, for example, the mouse vector, right? We can say glm vec2 mouse v. We can define this as being equal to mouse x mouse y. Okay, and then as the origin vector, we're going to set up with the mouse vector. We're going to set up the particle with the mouse vector. So let's run it. So the particle, it went to 0 because that's the default mouse position. I think just to demonstrate that this is correct, I can, for example, put here 500, 500. And you see, it changes there. I'm going to reset it to the mouse because it's going to be useful for us. We're going to have not just one vector, but many particles. So later we're going to be able to demonstrate this a bit more effectively. So we had a simple setup where the initial position was defined in the class, and now we're defining it in the main and sending it to the class. So quite often any interaction, main interaction, be it following mouse, etc., I define it in the of-app main class, and then I send the parameters to the class. So now we have one particle. What if we want to have what in a particle system is called an emitter? An emitter is a bit, it's a spot where the particles get born. It's like a fountain of particles, basically. So that's called an emitter in a particle system. So what if I want to not just one particle, but a fountain of particles that emanates all these, that generates all these particles, right? So to do that, I need a vector, not a 2D or a 3D vector, but a vector meaning a flexible array. So we're going to have a list of particles. In the beginning, the first particle will be particle 0, then particle 1, particle 2, particle 3, particle 4, particle 5. At a given moment, we're going to have n particles. We don't exactly know, but if we transform them into a vector, we can track then how many particles we have. So how do we transform a class into a vector? We simply add at the beginning vector, and we put the class between lower than, greater than signs. So it is a little bit kind of strange syntax, but that transforms a single particle into a list of particles, and they can be addressed using an array kind of syntax. So in of-app CPP, we're going to say that every frame, let's say, we're going to create a new particle. It's not just going to be on setup, it's going to be on update. So the setup, I'm going to move this code, which is the initial position for the mouse, etc. I'm going to move it to the update. I'm going to delete it from setup. I'm going to comment here, set up the particle, but I'm going to set up the particle now in update because I wanted this to be an animation, the setting up to be an animation, something that happens constantly. And particle is no longer just a single particle, it's multiple particles. So it needs to be under a for loop. For int I equals 0. And then I lesser than the number of particles we have in that vector. But how do we know that? Well, with vector we get a method for that to get the size. So it's particles, particle, that's the name of the vector, size. Sorry, my particle, right? My particle size. So that's the name of the vector, my particle size. And then I++, because we go from particle 0. Let's say particle size is 10, that we have 10 particles. So we need the for loop to go from 0 to 9, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and do all this to the particle, or the particle vector. So we're going to set up all the particles independently of how many we have there. Sorry, we don't need to set them all up in a for loop. We need to update them all in a for loop, so sorry about that. And I'm going to move this one here, because we're going to set them up individually and then we're going to update them collectively. So we're going to create first, we're going to create a new particle. We're going to say, I'm going to create, for example, here, after I get the mouse vector, which we can move a bit further down soon. So after we create the mouse vector, we can say, we're going to create a new particle, new particle, okay. And then we're going to set up that new particle. We're going to set it up with the mouse value. And then we're going to add the particle to the vector. And how we do that is with a command called push back. So we're going to say my particle, this is the vector, push back the new particle. Okay, so what's this going to do is the following. So we have kind of a, I have a typo here, my particle. So we're creating a new particle, we set it up with the mouse vector, and then we add it to the vector of particles. So basically we create this kind of newborn particle, we set it up, and then we push it back to the vector. Pushing it back means adding it to the bag, adding it to our container of different particles. And once we've done that, we can treat them collectively and update them all. Okay. And to draw them, we also need a for loop. So I'm going to draw them all at once inside a for loop. Okay. So let's see what happens here when we run this. We're going to see many particles being generated. So we could get rid of that initial default particle by just setting up particles if the mouse is not 0. Maybe that could be a good idea, just that we don't create particles unless we move the mouse, right? So we can say if mouse x not equal to 0, create a particle, set it up, and push back. Okay? And all this code gets moved here. So then we don't get this annoying particles on top. We only get the particles when we move the mouse. Right? So this is set up the particle is the first part, and this is update the particle. And maybe I went a little bit fast through this, and I changed the code a little bit around, so I'm going to revisit this. So in the beginning, we simply have a vector, the mouse position being tracked in a vector, right? Because as I mentioned in the previous exercise, I find vectors really useful to tidy up our code and to make our thinking a bit more logical. So here, first we create a new particle, and then we set it up, or we, in a more appropriate terminology, we run its setup function, and then we add it to the vector so that they can be then treated collectively. So when it's born, we give it their individual characteristics, right, through the setup, and then we add it to the particle to do this kind of collective operations, which is update and draw. If we use something in C++, we have something called constructors, where we could collapse these two lines into one. We could create the particle and set it up in one go. But I'm going to keep it more openFrameworks like, that we respect the setup, update, and draw. And the reason we're setting up the particle in update rather than in setup is that we don't want all the particles in the beginning. We want them to be born slowly, one by one. Slowly, I mean, in this case, it's 60 times per second. It's not that slow. So now we can tweak this a little bit. We can add a little bit of dynamics to the particles. So I can add some transparency to the particles. I can change the color, and I can change also a little bit the orientation. So let's tweak the particles a little bit. They're a little bit too boring. So first, the velocity is always 0 on the y-axis. Let's give it some variation in the y-axis. So of random. So if I want of random as a special code for of random between -1 and 1 is of random float. So float is something that usually the pure float number is something between -1 and 1. And something between 0 and 1 is an unsigned float, or UF. So in this case, let's give it a float of random f, okay, for the y-axis. Also, let's change the particle opacity a little bit, and also change its color. So let's have some magenta. Let's have some magenta particles, for example, 255, 0, 255. And then opacity, let's say something very little, like 10. So let's see how this goes. So now it looks a little bit better. Maybe opacity is a bit too low for this speed. What we could have is the particles bouncing back when they hit the wall. Also, at some point, we need to remove particles, because we can't have particles being added forever. We'll run into a wall in terms of processing capabilities, because openFrameworks C++ can manage, thousands of particles. But if you have many thousands, then it will probably slow down, right? And at some point, it disappears, so you actually don't need them. You can start removing them. How do we do this? So first, I want them to bounce back the right part of the screen. How would I check for it to bounce back? And I want to show you how to control individual points or individual coordinates in a vector. So if the particle hits the right edge of the screen, that means if pos v dot x, so the x of the vector, if pos v dot x is larger than of get width, which is the width of the window, right? Then change the velocity. If it's positive, change the velocity to negative without changing its value. The number itself, just change the sign from a plus to a minus. How do we do that? We can say val v dot x, multiply this by -1, so the positive becomes negative. How to multiply itself times 1? It's the same as adding itself times 1. So it's asterisk equals time equals -1. So we just invert the sign. What's positive becomes negative. Also the same is true. What's negative becomes positive. But in this case we have positive values becoming negative. So what happens here is that the balls will bounce off the right edge of the particles will bounce the right edge of the window, right? You see, so they are kind of hitting the edge and then coming back. Now, once they get out of sight, I want to remove them. Actually, to see them, I'm really going to put this alpha a little bit higher so I can see them better, from 10 to 50. So how do I know that they are being that I can remove them, or how do I know how many there are, and this kind of thing. So if we are treating them as a herd, as a collective, checking the herd and calling the herd if the numbers are too high, I wouldn't do it in the particle, right? I would do it from the kind of app. So the particle is the individual, and of app is the society, let's say. And if you want to manage the size of the group of the society of particles, then I would manage it in of app, not in the particle. So on update, what we could do here is that if the particle is going off the screen, if that particle is going off the screen, we could remove it. So let's say first I'm not going to use an off-the-screen value. I'm going to use an on-screen value so that I actually see I want to see them being removed. So let's say if the particles cross, they are going left and they cross pixel 100, let's remove that particle, right? So here on update, I want to say that if my particle I pause dot, so then we can access the pause v, and from the pause v we can access the x, is lower than 100, right? Then at least at first, let's just check what is the size of the herd, what is the size of the vector, and how many particles are there. So a really important tool for debugging is the console out command, so I can print some numbers to the console. So I can say console out means C out, or it's written like this. And then it's a funny syntax. It's lower than, and then the variable we want to track, or the expression we want to print. And in this case, it's my particle I size, right? So it's the size, not my particle I, my particle, the whole vector, sorry, not just that. So my particle I size, and then end line, okay? So we're not, I have a typo here, my particle. We're not deleting anything, we're just tracking. As soon as the particle goes out through the 100, So it should start, you see, okay. So now 300 particles have crossed the point 100 in my screen. So it's like I have a little gate there, and these are the number of particles that have crossed the gate. And I think soon you will start to see the application slowing down, because as we cross to the thousands, and even those, you have to imagine that those circles that even you're not seeing that have crossed the threshold of the screen, they are still there in memory, right? They are still being tracked by the computer. So you see the application slowing down. I hope that in the video you can also see this slowing down or perceive it. Now we're going to 2000 and it's really starting to stutter and not. So we need to remove them. We don't need to track 2000. We don't have 2000 on the screen. We have probably a couple of hundred on the screen. And that's all we need. The others can be removed from the vector. They don't need to be redrawn all the time. How do we remove it? With the term erase. And there's a funny syntax there that we're gonna check. So let's add it here. So my particles. So if that particle I has crossed the gate, we can say that my particle or my particles. So this is the vector. My particle erase. And then we want the position of the iterator. So the logical thing would be to say that, just erase I, because that's the iterator, but the syntax is a little bit more awkward. We need to give a position, we need the beginning of that position, which, the intuitive thing would say, oh, it's 0, the beginning of the vector is always 0, but in C++ we say my particle begin. So then it gets the beginning of the vector plus I. So every time this particle I gets out of the screen, let's say, we're going to start tracking it in pixel 100 so that we see it. We're gonna, from the vector, we're gonna erase the particle with index I or beginning plus I, which beginning is gonna be 0. That's always the beginning. But anyway, we're gonna remove that one, and that means that let's say when the particle that crosses the gate is particle 50, and I had 100 particles. It means that particle 50 is going to be removed from there. Then all of a sudden I have 99 particles, all the particles. So particle 51 becomes particle 50, particle 52 becomes particle 51. They all get adjusted, so there's no gaps. Otherwise the for loop wouldn't work. So when a particle item gets erased from the vector, the size of the vector gets rearranged. So let's run it. And let's see, and pay attention to the console, because we should not be getting these numbers 200 and something. So now you see you can see the particles being deleted, right? And you see that we have a couple of hundred particles on the screen, and so they're bouncing off the left edge and then they're being removed there. If you want to keep the illusion that they're still there, instead of having the gate at pixel 100, I would have the gate out of the screen, for example, in pixel minus 100. And that's about it. So 200 is perfectly manageable for openFrameworks without any or for simple or any type of delay. So that's completely fine. Of course, the more you move to this side, probably the more space you have, you get more particles. So that's about it. what I want to add to this exercise, to add a little bit more dynamics to the speed where things are going, is to add an acceleration to the velocity of the particle. And also I want to move the gate from 100 to minus 100. Maybe I want to I want the particle to bounce off not pixel 0, sorry, the pixel of get width, but of get width minus 50, so I see the bouncing becomes a little bit more visible. Now, how do I add an acceleration to the velocity? I need to create another vector. I'm just copy pasting that, and I'm going to call this one accel v. So this is very common in particle systems or in kind of generative graphics, that you have velocity and acceleration. Okay, so we have position, velocity, and accel v. Accel v, let's create a constant vector of, I don't know, 0.5. The acceleration will only occur in the x-axis, so the acceleration in the y-axis will be 0. Okay, so accel v is the acceleration vector. So with acceleration, before we add the position, the velocity to the position, we need to add the acceleration to the velocity. Okay. So increment with acceleration. So the velocity is gonna, instead of having this constant velocity, it's gonna speed up, right? So maybe the original velocity can be a bit lower, so that we see the speeding, really the speeding up. So between 2 and 4, maybe, something like that. So it's gonna go slowly in the beginning, and then it's gonna speed up. I have a mistake in my code, that they're bouncing back because the acceleration is turning again to negative, right? So when the position turns negative, I also need to when the position, sorry, crosses the border of the right, we also need to change the accel v x to -1. Otherwise, the acceleration is positive, the velocity becomes negative, and then the acceleration is positive, so it starts and they start to slow down and then turn the other way. So we also need to change the acceleration there. So let's run it and see what's going on. So you see it starts slow and then it really picks up speed, right? Maybe the acceleration could be a little bit lower value. And you see that the numbers keep quite, because now everything becomes faster, so we get less particles in the picture. So what I want to do is maybe slow down the acceleration a little bit. Instead of 0.5, maybe 0.1. And also have a larger spread, because everything becomes faster. I like the larger spread in the y-axis. So let's fine-tune that. So acceleration, maybe 0.1. And the random in the y, I'm going to spread it out from -1 to 1 to something like 5, maybe -2, 2, or even more. -3, 3, maybe something like that. So let's see how that works out. Too spread out in the y-axis, but I like the speed. I think I like the speed because you can really see the acceleration. Maybe a little bit faster and a little bit less wide. So we're almost there. Maybe something like this, and maybe something like that. And you see the numbers. So we're managing to cull all the numbers very, very nicely. Yeah, I think now it's looking a little bit more dramatic in a way. The acceleration, all the density, and I'm starting to be happy with this. Maybe the alpha could be tweaked a little bit more, a little bit less. Maybe I'd like to have a little bit more dense, more particles being generated per frame, and maybe, yeah, maybe that would be the trick, having more particles. I'm not going to go in there. We could go with this forever. It's kind of fascinating, right? But how we could have more particles or less particles being generated is the following. So when we create particles, we could have this inside a for loop. So instead of creating one particle per frame, let's say we want to create 2 or 3 particles per frame, we have a for loop between 0 and 3, or between 0 and 10 if we want, well, do 0 and 9 to have 10 particles. If we want to have less particles, I would add a modulo to the frame count, so that with only we count steps where we create particles only after 5 frames. So only for frame numbers that are multiple of 5 would you, if the frame number is multiple of 5, modulo frame number modulo 5 is 0, which is multiple of 5, then you would have the particle in class. If you want, we can check more variations of this. I think I forgot to mention, when we print to the console, I forgot to mention the end L is end line. So if we don't have end L here, so all the numbers would be glued together. So end L creates kind of a line break, right? So you can add multiple parameters here with lower, lower than, and then you see the end line is actually, now it doesn't even show everything. So end line is quite useful because it creates another line instead of merging everything together, right? Gluing everything together. And that's it. I'm sure that you'll probably have some questions about this. So if something we saw a lot in this exercise. So if there's some area which is not as clear, and that you'd want it to be explained a bit better, I'm happy to do that in class. We went through a lot. Just to recap what we went through, just looking at OVAP is quite simple, but it's just creating a vector, and OVAP just manages the vector, right? So what does this mean, managing the vector? We set up the particle by creating a new particle, setting it up, and adding it to the flock of particles, let's say, with pushback. By the way, pushback means add it to the end, to the back of the vector. So if you have a vector with 5 particles, meaning particle 0, 1, 2, 3, 4, you push back, so the new particle becomes particle 5, right? That's why it's called pushback. You can also remove the last particle with a pop back. Basically erases the last particle. And in update the particle, we are basically running its update, And also we are removing particles if they cross pixel x minus 100. And in the draw, we simply draw the particle. So you see, between particle CPP and OVAP CPP, we have quite a bit of code, but by keeping it into two separate files, it becomes really manageable, I feel, and it's much better to go between sections with files which are clearly named than scrolling in your code. So I like to keep the code compact and then split it into different files, different classes. It's much more manageable for you yourselves to look at your code in 1 year from today when you come back to this. So what did we do in CPP? So in Particle HPP, basically we just create the three main vectors that we need, that are main building blocks: the position, the velocity, which we'll add to the position, and the acceleration that we add to the velocity, right? And in Particle CPP, we just the setup is basically based on a certain origin, which is the mouse position. We calculate pos v. Then we also calculate velocity, which is random x always going right and random y going up and down, and acceleration that gets added to the will get added to the velocity in update. We add the velocity we add the acceleration to the velocity. We add the velocity to the position, and then we have a little code here to bounce back the velocity and acceleration if they hit the get width minus 50. This is just an arbitrary number to make the bouncing a bit more visible, which is based on the radius. But I didn't need to add it. Just a little flourish, and then we invert the direction. Actually, here it should be. I have a typo here. Glad that I looked at the code again. I'm not making velocity go to b minus 1. I'm inverting the sign of the velocity. So I had a mistake there. I'm glad I reviewed the code. So always like in the end, especially when I have a big exercise, to review what I'm doing. And draw is very simple. We just have a color and we draw the circle with that color. So let's just revisit our exercise with that revised velocity. So now the velocity should be a little bit more incremental. So it was jumping to 1 instead of multiplying by minus 1. It was jumping to minus 1, and now it's a little bit more fluid. And now I get what I wanted, which is more particles in sight. And that's it. I hope you enjoyed this exercise, and see you in the next one.